Section 1 Introduction. We're going to delve into the world of diffusion probabilistic models, a new and exciting type of generative model that's been making waves in the field of computer vision. Unlike other generative models such as variational autoencoder, VAE, generative adversarial networks, GANs, and vector quantized approaches, diffusion models offer a fresh approach. They use a fixed Markov chain to map the latent space, which allows them to capture complex structures within a dataset. These models have shown impressive capabilities, from the level of detail they can generate to the diversity of the examples they produce. This has led to significant advancements in various computer vision applications, including image synthesis, image editing, image-to-image translation, and text-to-video generation. A diffusion model consists of two processes, the diffusion process and the denoising process. In the diffusion process, Gaussian noise is gradually added to the input data until it's almost entirely noise. In the denoising process, the original input data is recovered from its noisy state through a series of learned inverse diffusion operations. Typically, a U-net is trained to predict the noise to be removed at each denoising step. While previous research has focused on using pre-trained diffusion U-nets for downstream applications, the internal workings of the diffusion U-net have not been thoroughly explored. In this paper, we aim to investigate the effectiveness of the diffusion U-net in the denoising process. To better understand the denoising process, we shift our perspective to the Fourier domain, an area that hasn't received much attention in previous research. We observe that during the denoising process, the low-frequency components of an image change slowly, while the high-frequency components display more pronounced dynamics. This makes sense when you consider that the low-frequency components represent the global structure and characteristics of an image, including its layout and color. Rapid changes to these components could fundamentally alter the image, which is not the goal of the denoising process. On the other hand, the high-frequency components, which contain the rapid changes in the images such as edges and textures, are highly sensitive to noise. Therefore, the denoising process needs to remove noise while preserving these important details. We also investigate the specific contributions of the U-net architecture within the diffusion framework. We find that the main backbone of the U-net primarily contributes to denoising, while the skip connections introduce high-frequency features into the decoder module. These connections help recover the input data, but they can also weaken the backbone's denoising capabilities during the inference phase, leading to the generation of abnormal image details. To address this, we introduce a new strategy called FreeU. This strategy uses two modulation factors to balance the feature contributions from the U-net architecture's main backbone and skip connections. The first factor, the backbone feature factors, amplifies the feature maps of the main backbone to strengthen the denoising process. However, this can sometimes lead to an oversmoothing of textures. To counteract this, we introduce the second factor, skip feature scaling factors, which helps to prevent texture oversmoothing. Our FreeU framework can be easily integrated with existing diffusion models and can be used in applications like text-to-image generation and text-to-video generation. We've conducted extensive experiments using Stable Diffusion, Dreambooth, Reversion, ModelScope, and ReRender as our base models for comparison. The results show that using FreeU during the inference phase significantly improves the quality of the generated outputs. In summary, our contributions are as follows. 1. We explore the potential of U-net architectures for denoising within diffusion models and find that its main backbone primarily contributes to denoising, while its skip connections introduce high-frequency features into the decoder module. 2. We introduce a simple yet effective method, FreeU, which enhances U-net's denoising capability by leveraging the strengths of both components of the U-net architecture. It significantly improves the generation quality without requiring additional training or fine-tuning. 3. Our proposed FreeU framework is versatile and integrates seamlessly with existing diffusion models. We demonstrate significant sample quality improvement across various diffusion-based methods, showing the effectiveness of FreeU at no extra cost. Section Summary. Diffusion probabilistic models are a type of generative model that have gained attention in computer vision tasks. These models use a fixed Markov chain to map the latent space, allowing for complex mappings that capture structural complexities in a dataset. In this paper, the authors investigate the effectiveness of the diffusion U-net for the denoising process and propose a method called FreeU that enhances the UNet's denoising capability by leveraging the strengths of its main backbone and skip connections. This method improves the quality of generated outputs without requiring additional training or fine-tuning and can be seamlessly integrated with existing diffusion models. Section 2: Methodology. Let's delve into our methodology. We'll start with some basics. We're working with diffusion models, specifically denoising diffusion probabilistic models, DDPM. These models have two main parts: a diffusion process and a denoising process. The diffusion process involves adding a bit of Gaussian noise to our data distribution, step by step, over a sequence of t steps. This is done through a Markov chain, following a specific variance schedule. On the other hand, the denoising process is about reversing the diffusion process. It takes the noisy data and cleans it up to get back to the original data. This process is guided by certain parameters, determined through estimation procedures involving a denoising model. This model is usually implemented using a time-conditional UNet architecture, which is trained to remove noise from data samples while also improving the overall quality of the generated samples. Now, let's talk about how the UNet architecture performs denoising. The UNet architecture has a main network, which includes an encoder and a decoder, and also has skip connections that help transfer information between corresponding layers of the encoder and decoder. We conducted an experiment to understand the role of the main network and the skip connections in the denoising process. We introduced two scaling factors to adjust the feature maps generated by the main network and skip connections. Our findings showed that increasing the scaling factor of the main network significantly improved the quality of the generated images. However, changing the scaling factor of the skip connections didn't seem to have much effect on the image quality. We found that the improvement in image quality was due to an increased denoising capability provided by the main network of the UNet architecture. Increasing the scaling factor of the main network resulted in a reduction of high-frequency components in the images generated by the diffusion model. This means that enhancing the main network features effectively strengthens the denoising capability of the UNet architecture, leading to better output in terms of both fidelity and detail preservation. On the other hand, the skip connections in the UNet architecture serve to forward features from the earlier layers of encoder blocks directly to the decoder. These features mainly consist of high-frequency information. We hypothesize that during the training of the UNet architecture, these high-frequency features may speed up the convergence toward noise prediction within the decoder module. This could potentially reduce the effectiveness of the main network's inherent denoising capabilities during inference. Next, we introduce a simple yet effective method, called FreeU, which enhances the denoising capability of the UNet architecture by leveraging the strengths of both the main network and the skip connections. This method significantly improves the generation quality without requiring additional training or fine-tuning. For the LTH block of the UNet decoder, we introduce two scalar factors, a scaling factor for the main network feature map and a scaling factor for the skip connection feature map. The main network scaling factor aims to amplify the main network feature map, while the skip connection scaling factor is designed to reduce the skip connection feature map. However, we found that indiscriminately amplifying all channels of the main network feature map results in an oversmooth texture in the resulting synthesized images. Therefore, we limit the scaling operation to half the channels of the main network feature map. This strategy enhances the denoising capabilities of the main network while avoiding the negative effects of a globally applied scaling, thereby achieving a better balance between noise reduction and texture preservation. To further address the issue of oversmooth texture due to enhanced denoising, we employ spectral modulation in the FreeU domain to selectively reduce low-frequency components for the skip features. Finally, the modified skip feature map is then combined with the modified main network feature map for subsequent layers in the UNet architecture. The proposed FreeU framework does not require any task-specific training or fine-tuning. The parameters of the architecture can be adaptively re-weighted during the inference phase, which allows for a more flexible and powerful denoising operation without adding any computational burden. This makes FreeU a highly practical solution that can be easily integrated into existing diffusion models to improve their performance. Section Summary. The methodology section introduces diffusion models, which consist of a diffusion process and a denoising process. The diffusion process introduces noise into the data distribution, while the denoising process reverses the diffusion to recover the clean data. The denoising process is implemented using a time-conditional U-net architecture, which is trained to remove noise and enhance the fidelity of generated samples. The section also explores the role of the U-net architecture in the denoising process. It is found that increasing the scaling factor of the backbone features improves the quality of generated images, while variations in the scaling factor of the skip connections have a negligible impact. Based on these observations, a method called FreeU is proposed, which leverages the strengths of both the backbone and skip connections to enhance the denoising capability of the U-net architecture. This method does not require additional training or fine-tuning and can be easily integrated into existing diffusion models. Section 3.1 Implementation Details. We've carried out a series of experiments to evaluate the effectiveness of our proposed FreeU method. We've compared our results with those of leading methods such as Stable Diffusion, DreamBooth, Model Scope, and ReRender. The beauty of our approach is that it integrates smoothly with these existing methods without adding any extra computational burden related to additional training or fine-tuning. We've strictly followed the recommended settings of these methods and only introduced the backbone feature factors and skip feature factors during the testing phase. Stable Diffusion is a well-known model that can create realistic images from text descriptions. It has shown excellent performance in various image creation tasks. When we integrated our FreeU method into Stable Diffusion, we saw a significant improvement in the model's ability to generate images. For example, when given the text, "A blue car is being filmed," FreeU improved the image by removing irregularities on the car's roof and enhancing the details of the surrounding structures. Similarly, when given the text, "Mother rabbit is raising baby rabbits," FreeU ensured that the image accurately depicted a mother rabbit caring for her babies. We also conducted a study with 35 participants to assess the quality of the images and how well they matched the text descriptions. Each participant was given a text prompt and two corresponding images, one created by Stable Diffusion and the other by Stable Diffusion with FreeU. The majority of participants preferred the images created by Stable Diffusion with FreeU, indicating that FreeU significantly improves the Stable Diffusion text-to-image model. Model Scope is a cutting-edge model that can generate videos from text descriptions. When we integrated FreeU into Model Scope, it improved the model's ability to create videos. For example, when given the text, "A cinematic view of the ocean," from a cave, FreeU enabled Model Scope to accurately depict the view from inside a cave. Similarly, when given the text, "An astronaut flying in space," Model Scope with FreeU was able to create a clear and vivid image of an astronaut floating in space. We also tested FreeU on various other tasks. For example, we integrated FreeU into DreamBooth, a model that specializes in creating personalized images from text. The results showed clear improvements in the realism of the images. We also integrated FreeU into reversion, a method based on Stable Diffusion that can invert relationships, and found that it improved the quality of the results. Finally, we tested FreeU with ReRender, a model designed for zero-shot text-guided video-to-video translations, and found that it improved the detail and realism of the videos. In conclusion, our results show that integrating FreeU into existing models can significantly improve their performance, leading to more accurate and realistic images and videos. Section Summary. The authors conducted experiments to evaluate the effectiveness of their proposed FreeU augmentation. They integrated FreeU with state-of-the-art methods such as Stable Diffusion, DreamBooth, Model Scope, and ReRender, and observed notable improvements in image and video synthesis tasks. The qualitative and quantitative evaluations demonstrated that FreeU significantly enhanced the generative capacity, image quality, image-text alignment, and synthesis quality of the diffusion models. Section 3.5 Ablation Study. We've introduced a feature called FreeU with the main goal of improving the noise reduction capabilities of the U-net architecture within the diffusion model. To evaluate the effectiveness of FreeU, we carried out a series of analytical experiments using Stable Diffusion as our base framework. In our figures, we show the relative log amplitudes of the Fourier transform of Stable Diffusion, comparing scenarios with and without the use of FreeU. These images show that FreeU plays a significant role in decreasing high-frequency information at each stage of the noise reduction process, demonstrating its effectiveness in reducing noise. We also extended our analysis by visualizing the feature maps of the U-net architecture. Our figures show that the feature maps created by FreeU contain more distinct structural information. This aligns with the intended purpose of FreeU, which is to preserve detailed information while effectively eliminating noise, thus aligning with the noise reduction goals of the model. We also evaluated the effects of the components within FreeU. Specifically, we introduced backbone feature scaling factors and skip feature scaling factors to delicately balance the feature contributions from the U-Net architecture's main backbone and skip connections. Our figures show the results of these evaluations. In the case of SD plus FreeU, B, where backbone scaling factors are incorporated during inference, we noticed a significant improvement in the generation of detailed images compared to using SD alone. For example, when given the prompt, a fat rabbit wearing a purple robe walking through a fantasy landscape, SD plus FreeU, B, generates a more realistic rabbit with normal arms and ears, compared to SD. However, it's important to note that while the inclusion of feature scaling factors leads to significant improvements, it can sometimes result in an undesirable oversmoothing of textures. To address this issue, we introduced skip feature scaling factors, with the goal of reducing low-frequency information and alleviating the problem of texture oversmoothing. As shown in our figures, the combination of both backbone and skip feature scaling factors in SD plus FreeU, B and S, results in the generation of more realistic images. For example, in the prompt, a synthwave-style sunset above the reflecting water of the sea, digital art, the generated sunset sky in SD plus FreeU, B and S, is more realistic compared to SD plus FreeU, B. This underscores the effectiveness of the comprehensive FreeU strategy in balancing features and addressing issues related to texture smoothing, ultimately leading to more accurate and realistic image generation.